Huh? What happened? Huh? Oh, okay, it works. Hello everyone, my name is Wei Luo, and I'm a postdoc from University of Arkansas from Roland Blash School. Today, first, I thank the organizer to give me a chance to give a talk. So today I will talk about the nonlinear Follow-Hall effects in ferroelectrics and its existence and non-valid electric control. Oh, sorry. Yeah. So the outline includes following parts. So let's first see the motivation. So in 2015, this theory paper predicts the nonlinear enormous Hall effects for electronic system. So it is for Fermi system, and the material should be non-magnetic and also Blake inversion symmetry, and it must be a metal. And what they predict is that if you add an electric field, AC electric field around the x direction, you will find there are electrical current along the y direction, which is perpendicular to the square of the electric field. So it includes two parts. The first part is a DC current, and the second part is the second harmonic generation, which is related with the frequency omega. And for these two parts, the second term of these two parts always equal to 0 for non-magnetic system, which is maintain the time reverse symmetry. So this term must be 0. And this term for non-magnetic system, this term always non-zero because the omega. The omega is a Berry curvature in reciprocal Brillouin zone. So this term is a topological term. It is a topological properties. And then after 4 years, this experiment confirmed their prediction. So for the two-dimensional tungsten tellurides, they add an electric field around the x direction, and they find a nonlinear Hall effect along the y direction, which is perpendicular to the magnitude of the electric square of the electric field. So there is a because the nonlinear enormous Hall effect must be matter, so it cannot coexist with ferroelectrics, limit their application in combined with the ferroelectrics. So here we talk about the Follow-Hall effect, which is implied the first order Follow-Hall effect. In 2005, the experiment observed the effect. So they add a temperature gradient along this direction, and they find there is a thermal current, which is caused by the phonon along this direction. And they add a magnetic field perpendicular to the XY plane. So this is the first order Follow effect. And after 5 years, this PIL theory paper confirmed, explained their experiment, which is caused by the spin Raman type spin following interaction. So there is a later question. So the nonlinear, this is the first order Follow-Hall effect. So our question is that nonlinear Follow-Hall effects, which is for boson particle. So if it exists or not, and if it exists, because the phonon is a boson, so there is a low concept of Fermi level here. So it can be insulator and or matter. It doesn't matter. So that means if it exists, it will coexist with ferroelectrics. And the further question is that if you reverse the polarization of the ferroelectrics, can you reverse the nonlinear Follow-Hall effects? So realize the non-valid control. And also the condition for the nonlinear Follow-Hall effect should be similar with for electron case. So first it is a non-magnetic, and another is a Blake inversion symmetry. Because if you Blake inversion symmetry, you will have a non-zero Berry curvature here. So the key point is a Berry curvature. So you must Blake inversion symmetry to get a non-zero Berry curvature in the K space. And then first, because the nonlinear Follow-Hall effect is not investigated before. So first we should prove if it's existent. So we build the theory of the nonlinear Follow-Hall effect for the first time. So this is a first order Follow-Hall conductivity, and this is a Berry curvature. This is a topological term. So the Hall conductivity always related to the related with the balance curvature. So this is the first order, and the C2 can be expanded like this, and this term is a dilogarithm function. You can reference this paper, and then this is the Boltzmann equation. This is the collision time, and this tau means the relaxation time for the phonon. Here, rho means the Bose-Einstein distribution function for phonon or for any bosons such as photon or what. And then we consider the steady state. That means this term should be 0 because it is a steady time term. And we consider relaxed time approximation. So that means the tau can be used as a constant. So in order to simplify our question. And then based on this equation, because this term always 0, because for the phonon, there is low mechanical force. So this term always 0, and you will, based on this equation, you get this here. Yeah, and the rho is a distribution function for phonon, and we can expand to rho 0 plus rho 1. Rho 1 is much less than the rho 0, and rho 1 you can get this. And then for the C2, if you get a rho expand rho equal to rho 0, rho 1, and you will get the C2 here, and put the C2 to here, and you will get the nonlinear second. Nonlinear means the second order phonon Hall conductivity here. You find it is non-zero here. And the nonlinear current, thermal current, which is caused by the phonon, also can write this. And for simply, we suppose A equal to Z and BD correspondingly, and you will get the GZ equal to this one. And for the red one, we call it PXY. This is a tensor. You can see this is X and this is Y. So it is a tensor. And delta Tx means the temperature gradient around the X direction. So you can see it is proportion to the temperature gradient square. So that's why we call it a second order or nonlinear phonon Hall conductivity here. Okay, so in order to calculate the nonlinear phonon Hall current, you need to calculate this term. And for and for this one, this is experiment can decide for the temperature gradient. And what we should calculate is PXY, the tensor. And how to calculate it? So first, you need to get the energy for the phonon for different branch of the phonon and the different Q point in the Brillouin zone. And you can use the Wasp and phonon. You use the Wasp and phonon to do this term. And for this term, partial rho and partial Qx, you can expand like this: partial rho, partial E, and partial E, partial Qx. And based on this based on this package 1 or 2, and because this is just for electrons calculation, here we calculate for phonon, we should revise this tool. And this term is a Bell curvature for phonon. So 1 or 2 cannot calculate directly, so we should revise it to calculate the Bell curvature for phonon. And this is an expression for the Bell curvature. So this is a velocity operates. And you can write it like this. I should note that the phi here, this is for electron case, but for phonon, you should replace the wave function by the mode of the phonon. And then let's see the example for the 3D ferroelectrics. We find the nonlinear phonon Hall conduction effect can be switched for any 3D ferroelectrics. For example, the lead titanium oxides. So this is polarization down, this is polarization up. And for here, you add a temperature gradient around the -X direction. This is the hot region and this is the cold region. So based on this, based on the nonlinear current equation, it's like here. So because these two polarization states are connected by the inversion symmetry. So under inversion symmetry, the Bell curvature doesn't change the sign. But the Q point in the Brillouin zone will change the sign. So then it is an old function under the inversion symmetry. So the GZ, if the polarization switch, the GZ should change the sign. So and then we calculate the PXY for this material, and you can see the temperature, because there is a temperature here, and also there is a temperature for the rho. Rho is a distribution function. It is implying a temperature here. So it must be a temperature. It must be a function of temperature. So the different temperature increase, it doesn't increase. I mean, it increases first and then decrease. So there is a optimized temperature to optimize to observe the nonlinear phonon currents. And then we also can calculate the pxy, or the function of frequency. And here we fix the temperature, for example. Based on this equation, you can calculate it. For low temperature, for 30K, because you just excitation of the low frequency of the phonon. So the high frequency doesn't have any contribution. So you can see here, for the high frequency, it is flat. There is no contribution. But if you raise the temperature for 210K, and then you can see this high frequency also has a contribution for the pxy here, or PAB. So we have improved. We have proved that for 3D cases, it always switch the currents, the thermal current. But for 2D cases, this is a little different. So it's mainly based on the Bell curvature for the 2D case. Because for 2D case, we only have the omega z, the Bell curvature along z direction. We don't have a omega x, omega y. So the omega z, it is a pseudo vector. It's a property like a spin. So it is an actual vector. So omega z changes the sign under the mx, my. So if for the 2D material, the omega z is along z direction. So if you have a symmetry of mx, the omega z will change the sign. But the omega z will maintain the sign under the mz. If you give a operator of mz, you will the omega z, the Bell curvature along z doesn't change the sign. So these properties make the 2D ferroelectrics is different from 3D for the nonlinear form for conductive current reverse. So now we fixed out if the two polarization states are connected by the mx or by the my, the gx, gy co-reverses the sign. But if the two polarization states are connected by the mz, it doesn't change, reverses the sign. So for 2D case is a little different from 3D case. Now we take an example for the 2D tin tellurides. So because this material, the two polarization state is connected by the my along this direction. So it can reverse the sign. You also can see the reverse for polarization positive and polarization negative state. The pxz always switches the sign. And this is the function of the frequency. And then we also take an example for this 2D ferroelectric, because these two polarization states are connected by mz. So we figure out the Bell curvature distribution in the K space. So for this case, it doesn't, the Bell curvature doesn't switch in any space, in any position, it doesn't change the sign. But for 2D tin telluride, it switches the sign, you can see. That's why for this case, you can switch the nonlinear Hall current. But for this case, you cannot switch the direction. And then because calculate the Bell curvature of phonon in the K space is not easy to converge. You need a very dense K point. So we test the converge. You can see almost 500 or 600 can converge the results. And in order to observe this effect, we propose this experiment setup. We first use the laser pulse to generate a temperature gradient along this direction. So this is a laser pulse, and it has a frequency omega 0. And because this is a nonlinear effect, it will generate a temperature gradient along this direction. But the omega, the frequency can change, can double. So it should have a 2 omega 0. And due to the feedback effect, along this direction, you have a temperature gradient. You will induce electric current along this direction due to the feedback. So you can detect a voltage with the 2 omega frequency here. So this we propose for experimental observation. Let's see the conclusion. So first, we give the equation for the nonlinear phonon Hall current. So this is what we get, the key point of this work. And we find the long-violet control of nonlinear phonon can be realized in 3D ferroelectrics and also some 2D ferroelectrics. And we also propose the experiment setup to observe the effects. I want to acknowledge the funding from the WBFF, from DFG, DOD, and this simulation calculated for Arkansas High Performance Computer Center. Yeah, that's all. Thank you so much.
Thank you. Thank you for more questions.
So I have another question. If you want to find the material with the large set, what material finding to look for?
You mean how the magnitude of the current, right? Yeah. This is a question. This is a good question. Okay, let's see the formula. Yeah, here. This is the formula for the current. So you can see it is complex. For electrons, it is very easy because it is just affected by few collector. But for phonon or for magnum, it is different. You can see it decided first by the temperature gradient. So that means for experiment, you can add a temperature gradient. If the temperature gradient is large, you work at a large magnitude on the JZ. But also it decided by the tau. Tau is the lifetime of the phonon. If the lifetime phonon is larger, you work at the larger JZ. And also it is decided by the material. It is a material dependent for PXY. The PXY is decided by the Bell curvature. So that means for your phonon dispersion, the Bell curvature, if the phonon dispersion has a large Bell curvature, you work at a large JZ. So this is very complex. And also it is decided by your temperature here, and also the energy of the phonon. So there are many factors here. Yeah.
Okay. Maybe one more question? I have some question. Okay. Thanks. Thank you.
Mm-hmm.
Now it's Veronica Kovakova from Luxembourg Institute of Science and Technology. The result on direct energy harvesting.
This one works?
Yeah, just together, maybe in the two sides.
Okay, everything. Okay.
This one. Let's see.
Yeah, there's one. Hello, everyone. Do you hear me?
You have to wait to hear if you need.
Now? Ah, okay. How about now? Yes, perfect. Hello, everyone. So my name is Veronica Kovachova, but it's very difficult to sort of figure it out from how is it